comprises of 3 sections. Question number 1, the 2 sections with question number 1, which is a question on climate and weather out of 60 marks. And then we have question number 2, which is geomorphology, which is specifically fluvial geomorphology with 60 marks. Then as usual, our 2 papers, both paper 1 and paper 2, they do have a section deal with geographical skills and techniques out of 30. Right, before we go into our paper, I need to highlight maybe a few aspects on what you should note when it comes to the instructions of your paper. Right, I will focus on instruction number 9 and instruction number 10. Those are the major instructions that I see most of the learners disregarding, and at the end of the day they fail to score the maximum possible marks because of them not complying to that set of instructions. Right, when you look at instruction number 9, it says of answering in full sentences, except when you have to state name or list or identify. Full sentences, it implies that you are supposed to give a full statement with what we call a factor. A factor is a geographical fact which will be answering the question which is asked. And then you have to qualify that factor by further giving details to the factor identified. So your statements should be full in the sense that we should have, for every point raised to as an answer to a question, it should have a factor, and the factor should be qualified, should be explained. Then if we check instruction number 10, it's also a very key instruction that is mostly disregarded by learners, and they'll end up losing marks for that. Units of measurements must be indicated in your final answer. For example, 1020 hectopascals, 14 degrees Celsius, 45 minutes. You should not disregard the units of measurement, because if the answer is just 1020 what? It can be 1020 kilometers, it can be 1020 meters, 1020 degrees Celsius. We don't know the unit of measurement that you are implying to expose as the answer for that particular question. So you should make a special effort to follow the instructions and do as what the instruction suggests. Right, without wasting time, let's go to our questions. Right, we are starting with our first question, question number 1, climate and weather. We are having a first part with multiple choice. Right, the first question is saying, in an urban heat island can be described as. Right, before we look at the answers there, I want to clarify on the urban heat island and a pollution dome, because those are 2 concepts which are usually interchanged but wrongly, or which are confused by most learners. Urban heat island, we are basically looking at an urban area whose temperature is higher compared to the surrounding countryside or the surrounding rural area. So whenever we have an urban area, because of the different factors that happen in an urban setting, we tend to find that the average temperature of an urban area is relatively higher compared to the temperatures of the surrounding rural area or the countryside. So that concept of the differences in temperature between an urban area and a rural area, that is what constitutes what we call an urban heat island. It's only a matter of temperature. We are worried about the temperature, the average temperature of an urban area compared to a countryside or a farmland. Right. So a pollution dome, on the other extent, we are looking at the concentration of pollutants in an urban area. Pollutants tend to concentrate in a given area, predominantly in an urban area, because of industrial activity and because of maybe the volume of traffic and all those activities that contribute towards emissions into the atmosphere. So if those emissions get to contribute into the atmosphere above the urban area, that is a pollution dome. So I think you can see the difference. Urban heat island is about temperature. An urban area having a higher temperature compared to a rural area. A pollution dome, basically we are looking at the concentration of pollutants of an urban area. So that's the distinction between those two. Right, so we do not need to waste much time. We go and pick our correct answer from based on what we have been discussing. Right, if you check our responses, this one is saying urban areas being cooler or colder than rural areas. This is typically geographically wrong. We cannot have an urban area having colder temperatures than a rural area. Or an urban area receiving more insolation than rural areas? No, it's not about insolation. Urban areas being warmer than rural areas. This constitutes to be the correct response because our worry is about temperature. An increase in temperature as you move from rural area to urban area? No. Right. Then we go on to the next question. Urban heat islands can develop because of what constitutes to an urban area to have higher temperatures compared to the surrounding rural areas. Right, in urban areas, we have so many factors that will contribute towards the rise of the average temperature in the urban area. Predominantly is because of built-up surfaces. If you check the surfaces that we have in the urban area, most of them are artificial surfaces. Like we have the tarmacs and we have the concrete surfaces. And we have so many buildings within an urban setting. Those artificial surfaces, they contribute towards the rise of average temperature in an urban area. And also, if you can check, comparing to the rural area, in rural areas we usually have the natural surfaces, the natural land surfaces. So if you check those two, their absorption capacity is not the same. In urban areas, we tend to have more heat being absorbed than compared to the countryside where we have the natural surfaces, which some of them are reflective. So the response that we are looking for here, we are looking for a response with factors that contribute towards the absorption of more heat in an urban area and ultimately the resultant higher temperature in an urban area. So urban heat islands can develop because of our correct response. Response number A, reduce the number of vehicles. This one is wrong. The vehicle emissions, they contribute towards higher temperatures. Reduce industrial activity. This is also wrong. Reduced industrial activity does not contribute towards high rise in temperature, but rather it contributes towards reduction in the temperature because industrial gas emissions, they contribute towards a rise in temperature by absorbing some of the heat. Larger open water sources, this is also wrong. Water bodies are reflective. That is why we tend to find that in the parks in urban areas, those areas for recreation, which have got vegetation and which have got water bodies, they are cooler compared to the other areas where there's no vegetation and where there are no water bodies, because water has got a cooling effect. As the water evaporates, it has a cooling effect. And also when you have vegetation cover, that also has a cooling effect because of the concept of evapotranspiration which happens, and also because trees absorbing carbon dioxide, which is one of the greenhouse gases, and releasing oxygen, which is also a coolant. So we tend to find that vegetative cover and water bodies, they contribute towards the reduction of an average temperature at a given point in an urban area. So the correct response is D for that question, which is larger artificial surfaces in the urban area. We have more artificial surfaces. Artificial, we are saying those ones are man-made, not the natural features. So the artificial surfaces are the ones responsible for the absorption of heat and contributing towards the rise in the average urban area temperatures. Then we move on to the next question. The following photograph shows dash due to a large glass surface in an urban area. You can see our glass surface is shown here. This is an urban building with a glass surface which is showing that effect there. These are sun's rays which are being reflected by this glass surface. Remember, glass surfaces are shiny, and shiny surfaces, they do reflect heat. So the correct response here is what? Is A. The albedo is the correct response. Evapotranspiration, we are looking at a combination of evaporation and transpiration. Insolation, we are looking at incoming heat radiation. Absorption, we are looking at surfaces that do intake incoming heat. So the correct here is albedo for number 1.13. Right, we quickly move on to the next question. A pollution dome located over an urban area would be dash and dash. Right, let me quickly illustrate how those two concepts differ. We have a pollution dome. Remember, I indicated what a pollution dome is in the onset. A pollution dome, we're looking at a situation whereby there is a concentration of pollutants over an urban area. So the nature of the pollution dome or the shape of the pollution dome differs from the day situation and from the night situation. Let me start by illustrating the day situation. During the day, if this is our urban area, these are our buildings, we are assuming these are our buildings in the urban area. Our pollution dome during the day looks like this. And it has got a very large vertical extent. If you can check here, it's high up in the atmosphere during the day. Why is it high up there? It's because during the day we have higher temperatures in the urban area. Remember, we've been talking about temperatures being high in the urban area, the urban heat island. These surfaces absorbing heat and contributing towards urban heat island. And as heat is higher in the urban area there, or in the center of the urban setting, we tend to find that the pressure is low inside the urban setting. There is high heat being absorbed here and leading to an urban heat island. The surrounding farmland has got low temperature and low temperature here. So now, because of the high temperature, we tend to find that we have low pressure being experienced. And here, because of low temperature, the pressure is relatively higher in the rural area and is also higher from either side of the urban area. So now we have pressure gradient. If you check between these two, this is a rural area with high pressure, this is a rural area, there is higher pressure, but in the urban area during the day there is lower pressure, and it leads to pressure gradient force operating surrounding in the urban area. There is air which is driven from high pressure surrounding rural area into the urban area, and that air converges within the urban area. It tends to converge here and it rises and it plumes upwards like that. And as it rises, it lifts the pollutants up into the atmosphere. Remember, the pollutants are coming from the industrial activities happening in the urban area. But as incoming air is coming to converge into the urban area, it tends to uplift these pollutants and they are elevated into the upper atmosphere. That is why we have the pollutants being scattered up in the atmosphere during the day. But at night, the situation is not the same as what happens during the day. This is the day situation of a pollution dome in an urban area. But at night, we want to look at how the pollution dome's shape changes and how the concentration of the pollutants will be like. So during the day, because we are saying the pollutants are being blown by the incoming air, which is driven by pressure gradient force from the surrounding rural areas, we tend to find that the pollutants are not concentrated, but rather they are scattered in the upper atmosphere. The concentration is limited during the day, which means the effect of a pollution dome is not highly felt during the day because the pollutants are convected upwards by the incoming air from the surrounding rural area. But let's look at during the night. During the night, we still have our urban setup, we have our buildings, but our pollution dome shape is now a real dome shape. It's now like this. And the pollutants now are concentrated on the lower atmosphere and even to the level of the buildings. We now have high concentration. Because remember, during the day we said our pollution dome is elevated. But now the pollution dome has been lowered. It's now lower. Why is it lower during the night? Right, you tend to find that during the night we have more of descending air. We have more of cold air which is descending from upper atmosphere. That descending air is going to force the pollutants further down to a lower altitude, and they will concentrate to the level of the buildings and to the level of even the people in the urban area. And that is where the effects of the pollution dome are felt, because of the concentration of the pollutants now, which are being driven or which are being forced downwards by strong descending air during the night. So during the day is elevated, is high up there, the pollutants are displaced vertically and are in the upper atmosphere. At night, the pollutants are concentrated because of the sinking air, which is forcing the pollutants further down. So basically that's the concept or the idea behind the pollution dome during the day and the pollution dome during the night. We have seen the differences in the shape and the concentration of the pollutants. It's elevated during the day because of that effect of incoming air from the surrounding rural area because of pressure gradient. It ceases to exist during the night. The low pressure which used to exist over the urban area during the day is no more there, because now there's no more insolation which was contributing to high temperatures and ultimately the reduction of temperatures within the urban setting. So during the night is now the opposite. We just have the pollution dome being lowered because of descending air, and apparently the concentration of pollutants will increase and it will affect the health and the activities of people staying in the urban area. So quickly, let's go to check our answers and find out the correct response based on the explanation that has just been given. Right, if you check the correct response, we should not waste time because I've explained the difference between those two. Our correct response for number 114 is response A. What is response saying? Response A saying? Response A is saying it's higher during the day. I think you can agree on that. We have indicated that. And also, the other correct response is lower during the night. So it's higher during the day and it's lower during the night. So that combination of item number 1 and item number 3, we find it on combination A. So our correct response for this question constitutes to be A. Right, we move on to the next question. This question here is on valley climates. I will quickly explain the valley climates so that we are able to interpret and justify how we got those responses, or how we are justifying those responses as the correct answers to the given set of questions. Right, we have a situation of valley climates. These are examples of microclimates. Remember, we have microclimates and macroclimates in geography. Microclimates, when we're talking of micro with MI, we are looking at the climatic conditions of a relatively smaller geographical space. For example, an urban area or a valley. That is a microclimatic situation. But if we are looking at a macro with MA, macro now that covers a wide area, we are looking at the climate maybe of the whole of South Africa, or we are looking at the climatic conditions of the whole subtropical region. That is a macro geographical space. Right, so when you're looking at valley climates, what you should note is the situation that happens in a valley during the day. It is not the same as what happens during the valley, during the night situation. I'll quickly explain the day situation and explain the night situation in as fast as possible so that we go to our responses and be able to figure out the correct responses and we move on with the discussion. Right, if we have a valley, right, I will start by indicating the conditions that happen in a valley during the day. Right, our valley situation, it occurs in this manner. We have our valley inclined like this. Right, I will make the illustration here. Right, this is our valley. This is our floor of the valley, and we have these are the sides of the valley, and this is another side of our valley. Right, what happens here? I also need to incorporate the concept of slope aspect here so that we touch on all those concepts. If you find them later in the discussion, we will just be familiar with those concepts. Right, we have what to call slope aspect. On slope aspect, we are looking at the orientation of the slope. Where is the slope facing? That has got an impact on what happens on the side of the valley. Where is the slope facing? This slope here, if let's assume we are geographically located in the southern hemisphere and our south is here and our north is there. If this valley is located in the southern hemisphere, our southern side is there and our northern side is here. Right, given the geographical knowledge of the location of the ITCZ and the general location of the position of the sun on a global scale, our sun is always located along the equatorial region. It varies between the 23.5 degrees north, which is the Tropic of Cancer, and it goes down to the Tropic of Capricorn at 23.5 degrees south. That is where our sun's overall position lies. So it means if we are in the south, our sun is always in the north. So we are saying if this slope is in the south, our sun is in the north. So if we check this position, if it's winter situation, because typical valley situations, we experience them during the winter season, where the sun's overhead position is lower. The sun is always in the lower atmosphere during the summer season. It does not reach overhead position in most places. So we are much worried about the climatic situations in a valley, typically during the winter season, because that is where we realize the effect of slope aspect being most dominant and being geographically pronounced because of the position of the sun. Right, if we check our sun's position, if there are sun's rays, insolation coming from the sun's rays are going to travel in a straight direction like that, in straight arrows like that, which will mean this part of the floor of the this slope of the valley here is the one that receives insolation. And what do we call this slope? This slope, we call it a north-facing slope in the southern hemisphere. It's north-facing, meaning to say its aspect is faced towards the northern direction. And this area which receives insolation here, which is on the north-facing slope, we call it the zone of incidence. It's called the zone of incidence. And this side, because it's facing away from the sun, this side of the valley, this is what we call the shadow zone. It's always in shadow because it's facing away from the sun. The sun's rays cannot curve to face this to hit this side, but it's facing away from the sun's direction. It's called the shadow zone. And in this shadow zone, we tend to find that we name it the south-facing slope in the southern hemisphere. So the north-facing slope in the southern hemisphere is the one that receives insolation, and the south-facing slope is faced away from the sun, is in the shadow zone, and does not receive insolation. And to name it differently, we should not confuse each other here. A north-facing slope in the southern hemisphere is also a south slope. When we are using direction, not orientation of the slope, when we are using the direction of the slope in the particular valley, this slope is on the southern part of this valley. Our south is here. And this slope, we call it a northern slope. It's on the north of this valley. But in terms of orientation, this is a north facing. So it's a north facing and a south slope. This one is a south facing and is a north slope. We should not confuse each other on those differences in naming the slopes. Right, I'll quickly illustrate again and show the day situation of our valley situation, and I'll quickly illustrate the night situation. We are still referring to the same valley according to the prescription of our inclination of our valley in the southern hemisphere. Right, what happens here? We are saying in this valley, we are having the two sides, the side which is facing to the south and the other side which is facing to the north on the same valley, and our valley floor lies here. So during the day, because of insolation, this side of the valley is going to be heated. It's receiving heat and is receiving insolation from the sun. The temperatures here are going to be higher compared to the floor. The floor does not receive much heat and sometimes does not even receive the heat. The sun's rays will hit the sides of the valley only and not the floor of the valley. So we need to use the relationship between temperature and pressure. If the temperature here becomes high because of the insolation, the pressure is going to be low. Temperature is going to be high here and the pressure is going to be low. The air which is immediately above this surface is going to rise because it has lost its density because of insolation. What is happening on the floor here is the temperatures are lower in the floor and the pressure here is going to be higher compared to the side of the valley. So we now have pressure gradient. There is higher pressure in the valley floor during the day and lower pressure on the valley side. So we tend to find that the air will move in that direction. We are going to have an up slope wind which is going to happen in the valley, coming from the valley floor going to the valley side. This is what we call the anabatic wind. These are what we call the anabatic winds, which operate during the day. They are upslope and they are called anabatic wind. And during the night, we check on what happens. During the night, the pressure system reverses. Why does it reverse? The insolation that was received during the day here is no more being received because the sun has set. At night, we no longer have insolation, but now we have long wave radiation or terrestrial radiation. We are losing the heat into space and into the atmosphere. The heat that was received during the day now is going back into space and going back into the atmosphere, which means now the valley side is now having excessively low temperatures. It has lost all the heat, but the valley floor is not affected as much as what is being experienced on the valley side here. So we tend to find that we now have a different pressure gradient force operating between the valley side and the valley floor. There is now higher temperature. There's now excessively lower temperature on the valley side because of long wave radiation, and the pressure now is higher here. Low temperature giving us higher pressure, and here the valley was not much affected. it's now warmer in the valley compared to the valley floor at night. So here we have relatively low pressure in the valley, and now the wind will reverse and go down slope. This is what we call the katabatic wind, which is typical of a night wind in a valley. It's downslope and it's called the katabatic wind because the pressure gradient has reversed and is now lower pressure in the valley. And these katabatic winds, they are also the ones responsible for the formation of what we call frost pockets. What are those frost pockets? You tend to find that on the valley floor here, we have accumulation of ice on some clear cloudless nights because of the incoming katabatic winds. These winds are very cold. They are originating from a ground surface which is very cold. They are cooled by the ground surface, and as they go down, they will condense, and sometimes the condensation level, if it's below the dew point temperature, is below freezing point, it will mean that the moisture in the katabatic winds are going to convert into frost because the dew point or the condensation point is below freezing point, which will mean that if the temperatures are below 0 degrees, maybe it's -2, -3, that will automatically lead that the moisture in that katabatic wind is going to freeze and is going to create frost conditions on the valley floor here, what we refer to as the frost pockets. And also the katabatic winds are also responsible for the formation of what we call the thermal belt. A thermal belt, we are saying, we end up having a belt here on the valley, on the upper part of the valley. This belt is a belt which is made up of warm air, but the warm air is trapped between two cold air masses. Right. This air mass below here is a katabatic air mass which has sunk from the valley sides, and it's very cold. But because of its density, it's more denser compared to the air which was in the valley. It will now displace the air which is warmer vertically up the valley slope because of the density effect. It's more denser, it's more heavier, it occupies the bottom part, and it uplifts the less denser air onto the sides of the valley, stretching from one end to the other. And also, why doesn't this air escape? Because you are saying a thermal belt is a belt of warm air which is trapped between two bodies of cold air. Remember, talking of winter situation, the Kalahari high pressure is very active during the winter season. We also have strong descending air. The strong descending air is going to force the thermal belt not to escape from the valley. So it's now trapped between this body of cold air and again this body of strong descending Kalahari high pressure air. So the thermal belt happens to exist like that. Then we also have the concept of an inversion. I think if we are to meet it in the discussion, let's just solve it here. The inversion, we are looking at the reversal of the normal temperature profile of the troposphere. We know that in the troposphere, the normal temperature profile or the normal temperature gradient, the higher you go, it should be getting colder. But when it reverses now, we are saying if you go to higher altitudes, instead of the temperature decreasing with altitude, the temperatures are increasing. So that reversal of the normal temperature profile or the reversal of the temperature gradient, which is normal, which we geographically know as the normal temperature profile. As long as you have that situation, we now have what we call an inversion situation. The temperature is now getting higher with altitude. So this situation is an inversion situation. Because if you check from this katabatic wind, the temperatures are cold. We expect the temperatures to keep on decreasing as we are going up with altitude. But however, we are meeting a belt with warmer air, which is above cold air. So that is an inversion situation. So basically an inversion, we are looking at a situation whereby we have warmer air existing above a body of colder air, which is not normal according to our troposphere situation. So whenever we have that reversal, we call it an inversion. So I think what we have explained here is going to assist us in answering some of the questions which are part of the valley climates. So we won't be discussing much because we have touched on all the concepts on the valley climates and the associated situations and associated winds on the valley because of those differences. Right. We need to quickly go to number 1.15. The wind illustrated in sketch A. If you check our sketch A here, right, check our sketch A. Our sketch A, you are seeing that we have an upslope wind. It's coming from the valley going up the valley sides. We have indicated that when we have that situation, we call it an anabatic wind. So our correct answer is C. We got number 116. The wind illustrated in diagram B is most prevalent. We've also discussed about this. Diagram B is showing a downslope wind. We said it happens during the night. So the correct response automatically is A. Right, we move on to the next question, which is the last question on the multiple choice section. Frost pockets, we've discussed about that. We said that is the accumulation of ice on the floor surface of the valley. What causes that? We're likely to form in diagram B, because what causes frost pockets to form in diagram B is response A, the accumulation of cold air. The cold katabatic air is the one that is going to cause the formation of the frost pockets. Whenever the dew point temperature falls below the freezing point, whenever we have maybe -1 temperature, -2, -3, that automatically will lead to the formation of frost pockets, because the dew point temperature is now falling below the freezing point. The moisture in the katabatic wind is automatically going to convert into ice, and the accumulation of ice on the valley floor is what we geographically refer to as the frost pockets. Right, I think we've done justice with the first part. We need to quickly move to the next section and see how best we can give the responses of those questions which will follow. So sometimes when you're answering multiple choice questions, before you attempt the questions, you need to acquire the basic knowledge about the geographical concept being asked there. Before you guess the answers, you need to have the right knowledge of what happens before you attempt those responses. Because sometimes you might try to use the odd one out, but if you don't have the right knowledge, that will be some form of difficulty. Right, let's move to number 1.2. Number 1.2 is saying the global wind belt responsible for the general movement of mid-latitude like cyclone is D. Right, that question, I want to illustrate the global air circulation model quickly, and we look at the general wind belts that we have on the global scale based on the existence of the different pressure belts that are distributed across the globe. Right, I will put an illustration of our globe quickly, and we will try to explain as fast as is possible. Right, basically this is grade 11. I think you still remember when you start grade 12, you refer back to grade 11 basics of the global air circulation model. Right, I will illustrate the global air circulation model using our major latitudes. Right, the major latitude here, dividing our globe into two, the north and the south. This is the 0, which is the equator, and we have our 30 to the north. We are adding our 60 to the north, and then we last have the 90 to the north, which is the North Pole. Then we add our 30 to the south, we have our 60 to the south, and we have our 90 degrees to the south. Right, what happens here? Because of direct insolation, we have a low pressure belt which forms along the 0-degree line of latitude, which is the tropical or the equatorial low pressure belt. Right, and we go to 30. 30 is a high pressure belt. Because of the sinking air, the air which rises here, it sinks in this particular belt, causing a higher pressure. The same happens around 30 degrees to the south. This is a high pressure belt. Then we move on to the 60 degrees north and 60 south. Right, this one here, because of deflective force which is experienced here. Remember our deflective frequency, which is caused by Coriolis effect. Right, is minimal around the equator, and it increases as we go towards the polars at 90 degrees north and 90 degrees south. So because of deflective frequency, we tend to have more air being deflected around 60 and leading to a low pressure belt developing, and also we have a low pressure belt developing. And because of intense cooling, which happens because of the latitudinal position of this North Pole and the South Pole, these places are located geographically very far away from the sun's overhead position, so that they have excessively low temperatures, and the pressure system which is dominant there is a high pressure on the North Pole and on the South Pole. Those are high pressure cells. Then you also need to have the knowledge of Coriolis effect. Remember, we have pressure gradient force. Pressure gradient force drives the air from high to low pressure. So if you are following pressure gradient based on those pressure belts, we must be having air being blown from high subtropical and high subtropical south going towards the equatorial low. And we must have another set of air being blown from the subtropical high going to the subpolar low, and again from the polar high going to the subpolar low. The same will happen in the northern hemisphere. From there, it must go that direction where there's low pressure and low pressure again. But because we are only not having a pressure gradient effect, we have combined the effect of pressure gradient and Coriolis force. That combination is going to cause what we call a geostrophic flow when they are in balance. When we balance pressure gradient force with Coriolis force, we get a situation of geostrophic flow. Right, what does Coriolis force do? Coriolis force, because the Earth is rotating, pressure gradient assumption does not hold true because the Earth is stationary. The body of air is moving over a land body which is also moving. So the air cannot go in a straight direction because it's moving over a surface which is also moving. So the air will tend to deflect in a given direction, will tend to bend in some given direction. That is the deflective force which is caused by friction. So if we check the sequence of deflective direction in the southern hemisphere, you should note this and never confuse this, because if you confuse this, you might never get anything correct. Deflective direction in the southern hemisphere is to the left. Winds are deflected to the left in the southern hemisphere because of the effect of Coriolis force. Then when we are going to the northern hemisphere, the deflective direction is different. Winds are deflected to the right. So because of this deflective direction, this wind which is supposed to come from polar south going towards the subpolar low is going to twist towards the left like that. And this wind again which is supposed to come from high is going to twist towards the left. And I think you can see the difference. Your left direction, if you are coming to from the south going to the north, is not the same as your left direction if you are coming from the north going to the south. That is why these arrows are pointing towards two different directions on this illustration. But both of them are pointing towards the west, towards the left. But the left coming from south going to the north is to another direction. And the left, when you're coming from the north going to the south, is pointing to another direction. But both of them are left deflections. Then if you check here, again, we have a deflective effect deflecting these winds to the left. So we have the planetary winds. This belt here is called the belt of the polar easterlies. This wind is originating from the pole region and is coming from, our west is always on the left, our east to the right. It's originating from the east going to the west. Remember, geographically we name winds according to their place of origin. So this is a tropical winds coming from the left coming from the east going to the west. So it's a polar easterly. Then these ones, they are named westerlies. They are blowing in the westerly, from the westerly direction going to the east. Then from 30 to 0, these are what we call the tropical easterlies. They are in the tropical region and they are from east to west. We call them the tropical easterlies, or they are called the trade winds. So when you're looking at mid-latitude cyclones, they occur when we're talking of our latitudinal values. We're looking at 0 to 90. Those are our latitudinal values. The midpoint from 0 to 90, I think you can see that is around 45. So we have what we call the polar front, which exists around this region. The polar front, that is the belt which splits these two different air masses. This air mass coming from the north is a westerly wind, and this one is a polar easterly. They cannot mix and they are split by the polar front. And that polar front is the one that is responsible for the formation of mid-latitude cyclones. So, if we are looking at these two, tropical easterlies, they do not have any effect on mid-latitude cyclones. They are further to the north here. The tropical region is around here. These ones, they don't influence mid-latitude cyclones. But the most definite response is these polar easterlies. But to be specific, when you are looking at the movement of mid-latitude cyclone or extratropical cyclones, their general movement direction is from the west to the east. What makes them move from the west to the east is they operate under the influence of westerlies. But for this question here, our correct response is polar easterlies, because for their formative stage, the polar easterlies are the ones which are actively involved in the formational process of the mid-latitude or extratropical cyclone, or what we also call the frontal depression. Right. Move on to the next question. This question is saying the diagram below shows the mid-latitude cyclone in the dash stage, initial or development. The initial stage of mid-latitude cyclone is not like that. The initial stage, we have a stationary polar front which is straight. When a mid-latitude is starting, it starts along the polar front which is undisturbed. In the initial stage, the polar front is not yet disturbed. It's straight. We have a straight polar front which is stationary, and we have the western is going in that direction, the polar eastern is going in that direction. That is the initial stage. The polar front is stationary, it's straight and is undisturbed. So this stage, you see that there is a wave here which is starting to form, which means we are now in the next stage of the formation process of mid-latitude cyclones. So this one is the development stage, or what we also call the wave stage, not the initial. The initial has got a stationary polar front which is undisturbed. It is going to be disturbed later on in the following stage of formation, either because of frictional drag between the two air masses rubbing against each other on the polar front. Right, I'll move on to the next question. The next question is talking about the diagram depicts a succession or a family of cyclones. A family of cyclones, we are looking at cyclones that occur in series, multiple cyclones that occur in the general same area which are in a series. But if you look at these ones, you cannot qualify that these are a series of cyclones. These cyclones are forming in multiples in the same general area of a relatively short period of time. So basically the correct response here is succession of cyclones. They are succeeding each other. They are forming in a short in the same geographical space over a short period of time. And definitely they will succeed each other. As one moves, the other one is going to occupy the space which has already been affected by the other. So the correct response there, we go for a succession of cyclones. Then we move on to the next question. The next question is talking about the mid-latitude cyclone again. Mid-latitude cyclones, you've got two fronts. We have a cold front and a warm front. Maybe to make it clear, a cold front, we are looking at a situation whereby we have cold air advancing towards warm air. If we have a body of cold air which is pushing towards warm air, that is what we call a cold front. And geographically, we use this symbol here as indicated. These are triangular inclinations which are added to this line here. They show that this is cold air. So it means from this side, cold air is coming from this side. It's advancing in that direction. So the boundary which is marking the zone between cold air from this extreme west going to the east is the cold front. So this one becomes our warm sector. So the warm sector, we are saying in this area here, we have warm air. And on this side, these semicircular inclinations which are also put on this line, they represent a warm front. And what is a warm front? That is a boundary where warm air advances towards cold air. So cold front, cold air going towards warm air. Warm front, warm air going towards cold air. And also what you should note, why the warm sector will narrow with continued development of the mid-latitude cyclone is because of the movement speed of the two fronts. A cold front is more effective compared to the warm front. Why? Because of the density of cold air. Cold air is more denser and can effectively push towards cold air, towards warm air, and it will vertically displace it. So that is why the cold front moves faster, because cold air is more denser compared to warm air, and the front moves faster, advancing towards a zone occupied by warm air. But the warm front moves slower because warm air cannot effectively push towards a zone of cold air because it's less denser compared to the cold air. And remember, in the southern hemisphere, we have clockwise circulation into the low. So our air will be circulating like that, meaning to say this whole area is made up of cold air. Right, let's go to our question. Front B, or B is here, we've discussed that. Correct response is warm. That is a warm front. Right, let's go to the next question. Right, the next question is on, we'll move on to the next question. Right, quickly. The next question is talking about the fronts again, but this is now a cross-sectional, not an aerial view of the weather system is now shown as a cross section. Right, we have our cold front, I think you can see there, and the cold front is having this towering cloud. Let me explain everything here before we answer any questions so that we can finish in the shortest possible time. Right, the cold front has got a steeper gradient. If we are to draw a cross section of a mid-latitude cyclone, not the area that we're using, it looks like this. This is our ground surface, and this is our warm front. So this being our ground, we are saying this weather system is moving in that direction from west going to east. There is cold air here and there is warm air here. And because of clockwise circulation, we also have cold air ahead here. And remember, we said the cold front, it moves faster compared to the warm front. This air here, which is in the warm sector, is gradually going to lose its space close to the ground because cold air is moving faster towards it, and it is failing to move as faster as it's being pushed from behind. So where will it go? It's failing to push cold air ahead of it the same way it is being pushed from behind. So the only way for this warm air to exist is to uplift itself and occupy the upper atmosphere. But because of the difference in the gradient of these two fronts, this one you can see it's steep and this one is gentle. The warm front is basically gentle. The upliftment that happens here is almost vertical because of the steeper gradient, but the upliftment that happens here is gentle, meaning to say condensation will start maybe here and will continue because the air is forced to rise vertically. This is going to lead to the creation of towering clouds of large vertical extent, like this one that you are seeing here. This cloud is got a very large vertical extent. It's very tall. It's a very tall cloud because of the strong ascendance of air, which is caused by the steeper gradient of the cold front. But here, the clouds that are going to form, we will have clouds which are more gentle, like this one here. So this type of cloud is what we call the cumulonimbus. Cumulo meaning to say a heap. It's a heaped cloud. You can see that the shape is heaped and heaped and heaped upwards. And nimbus, this is a Greek term for rain. So it means it's a towering cloud. It's a heaped cloud which is rain bearing. That is why the cumulonimbus is a heavy rainfall bearing cloud which is associated with thunderstorms. We have very heavy rainfall forming under this cloud cumulonimbus here. But this one here, we tend to have more of the nimbostratus clouds. Stratus meaning to say they are in layers. We have layered clouds, but they are also nimbo, meaning to say they are rain-bearing layered clouds, but not heaped as the cumulo. So we have the cumulonimbus, the heaped cloud, which is rain-bearing and which produces very heavy rainfall. But we also have this one here. It also produces high amounts of rainfall, but it's not heavy as this one here. It's steady rainfall, which lasts for longer periods. Because if you check the nature of this cloud, it's not the same as this one. Right. So let's go to our questions and attempt to answer. Why is this one also not heavy, not towering? It's because of the gradient. You are seeing how it is forming. It's forming over a gentle gradient. It's forming over an area which is not having vertical upliftment. So the cloud cannot be a towering one. Rather, it's a lower line. It's a layered cloud, which also produces steady amounts of rainfall and relatively over longer periods. The cumulonimbus does not last for long. Why doesn't it last for long? Because it will be driven by the movement of the cold front. The cold front, as it moves, it is going to drive the cloud. More and more air is going to accumulate and shift the position of the cumulonimbus cloud towards the warm sector. But because the warm front is not as fast as the cold front, we have lengthy periods of time forming on the side of the warm front under the nimbostratus cloud, like what is being shown here. Right, basically that's the idea behind the formation of those two clouds and the associated weather. Let's look at the implication on, let's go to the question rather and answer the question directly. We have discussed what F is supposed to help us in answering those questions. We just have to figure out the correct responses and move to the next aspect of discussion. Right, the first question is saying nimbostratus or cumulonimbus clouds are most likely to develop at A. We've answered that. The correct response is the cumulonimbus. according to the description that we have given, is the cumulonimbus, which is at A. It's a towering one. It's a tall cloud. Then gentle rain can be experienced at B because of cold air or warm air rises steadily above the cooler air. Here is warm air. Condensation takes place because of the upliftment of warm air, not because of cold air. Cold air doesn't have capacity to contain moisture, so it does not cause effective rainfall. Right, we go to the next question. Occluded front depicted in diagram C is a warm or cold front. In diagram C, we want to check the nature of occlusion, which we are realizing there. Right, our occlusion, we check it at the bottom of these two lines here. We are seeing this line here is coming from there, like that. And this line, which is coming from here, which is our cold front. So our occlusion, we see it from this point, going to the ground surface. The name of the occlusion is determined by the front which is touching the ground surface on that occlusion. So in this instance here, if you check on our occlusion, on that illustration, we tend to find that it is the cold front which is persisting and going to the surface. So if it's the cold front which is persisting and which is touching the surface, we call it a cold front occlusion. So the difference is basically like this. A cold front occlusion is like this. If the ground is there, the warm front starts up. But if it's a cold front occlusion, if it's a warm front occlusion, it's warm air which is going to the ground and the cold front starts there. So I think you can see the difference. This part is touching the ground and this part is touching the ground. Cold front touching the ground, cold front occlusion. Warm front touching the ground, warm front occlusion. Right, I think it's clear. We move on to the next question. The occlusion diagram C, we have shown that through the discussion. The occlusion, a cold front occlusion, is a result of cold air that moves. How does cold air move? It moves faster. Cold air moves faster because of its density. The cold front, we've discussed that it advances faster towards warm air, and as a result, we have faster movement on the side of cold air, and it undercuts warm air, completely dominating the ground surface. Right, we move on to this question here. Question based on moisture front. Maybe we just want to have a quick discussion before we answer the questions. Right, the situation that happens with the moisture front is, this is a typical traveling disturbance that happens during summer over the interior of Southern African subcontinent and mainly affecting the weather in South Africa in summer. Right, the moisture front and the line thunderstorms, they happen because of the existence of the subtropical anticyclonic weather system that happen to affect South Africa. I think you remember the three high pressure cells that we have that affect the weather in South Africa. The two of them are indicated here. We have to the east, we have the South Indian high pressure. That is the anticyclone which affects the weather system in South Africa and Southern African subcontinent. And also to the west, we have the South Atlantic as indicated here. And also we have another high pressure cell which we typically experience over the interior here. That high pressure cell is called the Kalahari high pressure cell. It's the one that dominates over the interior. So maybe before we answer the question, we need to analyze how these anticyclonic circulations cause traveling disturbances over the interior during the summer season. The Kalahari high pressure cell has got a typical movement direction. The Kalahari high pressure cell, we call it its movement a vertical displacement. Vertical displacement, which means in some particular season, it's close to the ground surface, and in some particular season, it's elevated up in the atmosphere. So the Kalahari dominates the interior in winter. That is where we have strong descending air, and we have high pressure dominating over the interior. But during summer, we have the Kalahari being up in the upper atmosphere. We have a weaker descending pattern because of intense heating over the Earth's surface. There is more of convectional currents being experienced over the Earth's surface, and there is weaker descending air. So the Kalahari, we say it is vertically displaced, and it is replaced by the thermal law. if it's hot during the summer season, we have a typical low pressure cell that we find over the interior here, which we call a thermal low. Thermal in the sense that is caused by extreme heating which happens over the Earth's surface because of high insolation. Right. Then these ones, these two, the Kalahari and the South Atlantic, they also have what we call a latitudinal shift. They shift with the movement of the ITCZ. If the ITCZ is further to the north, it means it's winter for us in the southern hemisphere. The South Atlantic, it moves further to the north, and the South Indian, they also move further to the north. But when it's summer in the southern hemisphere, the ITCZ is further to the south. They also move and go down somewhere here. So they are going up during summer, and they go down during during summer, and they go up during the winter season, following the ITCZ shift because of the different seasons. Right, let's go to our questions. So the formation of the moisture front is caused by the air which is driven out of the South Atlantic high pressure and the South Indian high pressure. And remember, the circulation that happens outside of the anticyclonic weather system is the opposite of the cyclonic weather system. We said when we have low pressure cells, which is the cyclonic system, we have clockwise circulation in the southern hemisphere. But when we have an anticyclone, the circulation reverses. It now becomes an anti-clockwise circulation outside the high pressure cell. Air being driven out of high pressure cell, it circulates anti-clockwise. That is why you are seeing these arrows. They are anti-clockwise, and also here it's anti-clockwise. So because of the existence of the warm ocean current here, the warm Mozambique current over the Indian Ocean, the air which is going to be driven out of the South Atlantic high is going to be warm and moist. And also the air which is going to be driven from the South Atlantic here, because we have the cold Benguela current operating over the Atlantic Ocean, we have cold and dry air being driven from the South Atlantic high pressure cell. And given the two differences of the two properties of the two properties of the two air masses, one is cold, one is warm, that is temperature. One is dry, the other one is warm. The other is dry, the other one is moist, that's humidity. Those two air masses cannot mix. And also because of difference in stability, this cold air coming from this side is more stable, has no tendency of rising, but this one is unstable, is less dense and can rise. So because of those differences in their properties, whenever they meet, they cannot effectively mix. They are split by a boundary, and remember, a boundary geographically we call it a front. So we have the formation of the moisture front. When these two air masses meet, this is what you are seeing here. So a moisture front, basically we are saying this is a boundary splitting the cold and dry air coming from the Atlantic Ocean and the South Indian warm and moist air as they meet over the interior. And also what allows these two air masses to filter into the interior is the vertical displacement of the Kalahari high pressure cell that we have mentioned earlier on. The Kalahari high pressure cell causes an invasion layer which will block the incoming air here if it's winter. That is why we have typical dry conditions over the interior in winter. We cannot experience this traveling disturbance in winter because the air which is supposed to filter into the interior and cause the wet conditions is blocked by the invasion layer as a result of strong descending Kalahari high pressure cell. But because it's weaker during summer, it's elevated, it lifts the invasion layer and allows for the filtering in of the warm moist air and the cold dry air from either side of the moisture front. Right, that is basically the idea behind the moisture front and the line thunderstorms. And the other thing, maybe you should also note where we have the line thunderstorms. The line thunderstorms, we have them lining on the east of the front. Why on the east of the front? Is because that is where warm and moist air is coming from. As the two air masses meet, the cold air undercuts, the warm air uplifts, and condensation happens predominantly on the eastern part. That is where the line thunderstorms will form. Right, we go to the questions. The first question is saying, what is a moisture front? We have defined that. The moisture front, basically, if you are to define it, we are defining it as a boundary splitting two air masses of different moisture content and temperature. In this instance, we are looking at air which is coming from the warm Mozambique current and air which is coming from the cold Benguela current here. These two air masses are meeting here. This is the moisture front. and this is associated with the heavy rainfall. So it's a front. The term moisture, it implies to rainfall. So basically it's a boundary between the two different air masses, which results in precipitation being realized on the eastern side of the front. That is basically how you can fully define, address the concept of moisture and address the concept of a front. A front, we know, is a boundary, and moisture here is referring to precipitation. So what kind of a boundary? Is a rain bearing or is a precipitation bearing boundary, which happens as a result of the meeting of the warm and moist air from the warm Mozambique current and the cold Benguela current, which is driven by the South Atlantic. Right, it's a concept, but basically you should address the basics of the concept. Right, we move on to the next question, number 132. State one piece of evidence from the diagram indicating that line thunderstorms are occurring. What piece of evidence from the diagram? We are seeing this. The conventional symbol that we use for thunderstorms, I think you must be aware, because that is grade 10. The conventional symbols that we use when we are interpreting weather, when we are doing synoptic weather maps, this symbol represents thunderstorms. So if you can see, we have 1, 2, 3, 4, 5, 6, all of them on the eastern side of the front. So that is clear evidence that we are having line thunderstorms there. They are indicated. Right. And they are on the east of the moisture front, like what you are seeing there. And in series, they are appearing one after the other in a line along the eastern part of the moisture front. Right, move on to the next question, number 133. Use information from the sketch and explain why there will be more clouds located on the eastern part instead of the western part. I think we've discussed that. Why we have clouds on the east is because that is where condensation takes place, because of the upliftment of warm and moist air coming from the South Indian high pressure. The situation, I think you know, is basically the same as what we were discussing when we were talking of mid-latitude cyclones, when we have a cold front uplifting warm air from the warm sector. It's basically the same idea, but here we are saying there is cold air coming from this side, it's more denser, and there's warm air coming from this side. The front is here between the two. This one is being forced to rise, this one is sinking. What is going to happen? This one, as it rises, clouds will form, and clouds are going to produce rainfall. Where are the clouds? The boundary is here. The boundary is there. That is where the front is, the moisture front. But the rainfall is on this side, where the warm and moist air is coming from. So that is basically the reason why we should say clouds are located. So your argument should state that the warm and moist air is the one responsible for condensation. And the warm and moist air is coming from the east. It's being forced to be uplifted because of the denser cold air coming from the west, the southwest. And as a result, we have cloud formation on the eastern side of our moisture front, and also the line thunderstorms existing on the eastern part. In a paragraph of 8 lines, question number 134, explain how the summer location or position of the high pressure cells or anticyclones promote development of line thunderstorms. We have elaborated on that earlier on, but just for the sake of clarity, we can just indicate the points there. What you need to note first when you're answering that question, you should know your 3 high pressure cells and how they affect that. The Kalahari high pressure cell, we said it's vertically displaced. If it's summer, the Kalahari high pressure cell is up in the upper atmosphere. It is weak. There is weak descending air. So how does that contribute towards that weather system being developed? If the Kalahari is vertically displaced, it also means the inversion layer is above the plateau. Is another argument. Inversion layer is above plateau because the Kalahari high pressure cell is weak. And what is the implication of that? The South Atlantic high pressure and the South Indian high pressure, how are they going now to be effective? They are now going to be effective in feeding in moisture and cold and dry air into the interior because of the inversion layer which is above the plateau. And therefore, the 2 air masses will effectively meet over the interior, leading to the development of line thunderstorms and the moisture front. I think you can see the argument there. You are explaining how those cells will impact on the formation of line thunderstorms and the moisture front. First is the Kalahari high pressure cell's position. It's weaker, it's up. It's allowing the invasion layer to be uplifted and leaving the plateau clear so that the feeding in of this air from these cells. And also remember, we talked about the movement of these cells. These cells, it's a summer, they are somewhere around South Africa. They can effectively now feed in air over the interior because of their latitudinal position. Remember, we said they shift latitudinally to the north and to the south. If it is southern hemisphere summer, the ITCs that is to the north of the equator, they are also further to the north. But when it's summer, southern hemisphere, the ITCs that is to the south of the equator, and they also shift down towards around South Africa. So they will also be effectively feeding in warm and moist air from the east and cold and dry air to the interior because of their position. So basically, you have to relate those three anticyclones. You should have the knowledge of those three anticyclones, and you should apply it to the given traveling disturbance which happens during the summer season. Right, that was question number 1.3. We'll move on to the next question. The next question is basically on what we have also been discussing. Basically, the things are interlinked. Right, we've been talking about cyclones, and basically cyclones are low pressure weather systems. We've been talking about a mid-latitude cyclone. We talked about its formation, and we talked about its movement direction, and we looked at how why does it come to that movement direction, and how does it come to its existence. We've talked about those ones. Now we are looking to into another type of a cyclone, which is also a low pressure system, which is a tropical. The only difference here is mid-latitude cyclones, they are occurring or happening in the mid-latitude region. They are happening in the mid-latitude region, and they do have a clockwise circulation, which is caused by the presence of the cold front and the warm front. But with tropical cyclones, they are now typical low pressure weather systems that exist within the tropics. Remember, our tropical region, we are looking at regions around the equator. So this is where we experience our tropical cyclones. Right, without wasting time, there's an infographic here with the path which shows how that tropical cyclone Freddy moved from its place of origin over the Indian Ocean as it gets over Madagascar, getting towards Africa and specifically into Mozambique and Malawi. Right, and also there's a satellite image. And also, if you check, what you need to note of a satellite image, you need to know the difference between the conventional symbols that we use for the mid-latitude cyclone and for the tropical cyclone. Right, our tropical cyclones, they are indicated, they are illustrated the same, not the same rather, they are illustrated somehow differently, but the symbol is basically the same, but its direction is different from the north position and the south position. Right, if you are looking at tropical cyclone, which is happening in the southern hemisphere, remember the circulation is clockwise in the southern hemisphere. So our tropical cyclone is illustrated like this. And if it's a tropical cyclone in the northern hemisphere, we say the circulation into a low pressure cell is anti-clockwise. It will be shown like this. That is the only difference if you are using synoptic weather maps and they are tropical cyclones which are indicated there. You should know that this is a southern hemisphere tropical cyclone. This is a northern hemisphere tropical cyclone, based on the differences of the rotors of our weather system symbol. Right, and also if you check here, our satellite image is showing clockwise circulation into the low. You can see that these clouds are wispy going towards a clockwise direction. Like what are we saying here? We are saying if you check the inclination of these clouds, the clouds are inclined in that direction. You are seeing like that. The clouds. This is showing that the system is circulating in that direction, which is clockwise. And this part here is the central part of the system, which is the eye. So you should be also familiar when you are reading satellite images. These are clouds which are shown and are indicating that the weather system is circulating. And how is it circulating? It's in a clockwise direction because it's in the southern hemisphere. And the clearer part of the weather system, this central part, that is the eye of the system. And clearly it shows that that system is fully developed because the eye is very clear. When you see the eye being so clear like this, as indicated here, it means the system has fully developed. Right, let's go to the questions. According to the infographic, I think you'll go through the infographic. According to the infographic, what was the lifespan of Tropical Cyclone Freddy? That is extraction question. The answer, you get it exactly from the given infographic, from the text. It says more than 5 weeks, according to what was indicated in the infographic. So the response for that question, we find it here. It says deadly storm, weekend workout, exceptionally long-lived. Right. The response is it was an exceptionally long-lived and deadly storm that traversed Southern Africa, Indian Ocean for more than 5 weeks. Our response is here. It lasted for more than 5 weeks. That is where we're getting our response for the first question. Move to the next question. Quote an example of infrastructural damage caused by Tropical Cyclone Freddy as mentioned in the article. We are quoting here, which means we are just going to extract information which is relevant to our question. Our question is based on infrastructural damage. Infrastructure, we are looking at those facilities which are necessary for the economy to function. The facilities necessary for production of goods and services to take place in an economy. We talk of road networks, we talk of communication networks, we talk of buildings, we talk of rail networks, we talk of buildings and all those forms of infrastructure. So we are worried about where there is only an indication of infrastructural effect. So if you check here, you can see that it says the nation's power grid was crippled. Its infrastructure, the power grid, we are looking at supply of power, electricity. It was crippled, it was damaged by the cyclone. It's one. And also if you check here, hydroelectric dam rendered inoperable. It's also infrastructure. The dam is used to generate electricity. So it's also an example of infrastructural damage, which would have happened in that particular context. And if you also check here, damaging many homes, you can also qualify. Right. Let's go to the next one. What suggests, describe the rotation of winds as depicted in the satellite image. We have shown that the wind is circulating in a clockwise direction. We are in the southern hemisphere. In the north is the opposite. Right, move on to the next question. Suggest 2 possible reasons why Tropical Cyclone Freddy intensified from a category 3 to 5 between 11 February and 19 February. If we check here, it was category 3 here, and it became 4, and it became 5 as it was moving across the ocean. Then it weakened over Madagascar, like what we are told. It re-strengthened over the Mozambican channel, and it became more stronger and affected Mozambique and Malawi. Why did it transform from here to here? Why was it changing the category? By category, we are saying the wind speed was increasing and its intensity was also increasing. So we want to look at the reasons which are favorable for the intensification of tropical cyclones over the ocean. Right, we can talk of the warm ocean currents, which is responsible for the fueling of the tropical cyclone. They need relatively higher temperatures for them to intensify. So this is a warm ocean current. This is a warm ocean over the Indian Ocean. It can contribute towards the intensification. Or we can talk of high humidity. Tropical cyclone, they need humidity for their development. So we have high amounts of humidity over the ocean. They are also contributing towards that. And also we can talk of the release of latent heat as condensation takes place. Because remember, tropical cyclone, they need the release of latent heat. So latent heat is also released as condensation is taking place over the ocean. That is why it was intensifying rather, as it was moving from 11 February to somewhere 19 February. Then we'll go to the next question. The next question is saying, suggest 3 strategies that the local, what could have caused the rapid weakening of tropical cyclone Freddy when it made a landfall in Menancheri? Right, that one is a land body. Why do tropical cyclone weaken as they go over land? That is the question. Right, number 1 is frictional drag. There is friction that happens over land. Remember, over water, it's a smooth surface. It's an even surface which is smooth. The system can intensify. The circulation can be effective over water, but as it gets over land, there is frictional drag that is going to happen. There is friction. So that friction has got an effect of reducing the intensity and weakening the cyclone. So friction can be one reason. We explain it in detail. And besides friction, you can talk of limited moisture. We said the system is strengthened by the feeding in of moisture. There's no more moisture over land. It got over land. There are fewer water bodies over land which can feed the system and make it stronger as it used to be. So there's limited moisture, and also you can talk of cooler temperatures over water, over land. We said it needs relatively higher temperatures for it to intensify. So, but over land, it's cooler. So it contributes towards less energy for the system. Those are some of the reasons why we can say the system will weaken as it gets over land. Then move on to the next question. Next question is based on this sketch here. This sketch not the strategies that can be used. There are so many strategies here that can be used by authorities in Mozambique to prepare for the destruction caused by tropical cyclone. To prepare for the destruction, what can the authorities do? We can prepare through early warning systems. I think early warning systems are very important. Notify people of the pending calamity. They should be prepared for it. So we talk of early warning, right? Explain how the early warning systems are going to assist. And we can also talk of evacuation plans. We take people to safer places or high-lying places so that they are in safety. Or we can talk of storm-resistant construction. For example, our infrastructure, it should be reinforced so that it resists the effects of such weather systems. Or we can also talk of emergency response. And also you can talk of maybe public awareness and education. Let people know, give public awareness and education to the people so that they know what to do and what safety measures are to take given the coming of the cyclone. So basically there are so many strategies that could have been implemented for the sake of tropical cyclones. And remember, tropical cyclones are the most destructive storms on earth. They are destructive because of their strong winds and their heavy rainfall. So whatever we do, we need to ensure that people are safe and are prepared for the coming of such a weather system. Right. This one I'm not going to waste time. We've explained this. This is related to what we have been talking previously on the question on the traveling disturbance. This is the invasion layer. An invasion layer, we've discussed about it earlier. We are saying an invasion layer, this is a layer of warm air which is above a cold air. And this invasion layer here is going to block the incoming moist air. If you see here, our invasion layer is touching the plateau here. This is our interior of South Africa, and this invasion layer has been forced lower and it's blocking the incoming warm and moist air from the Indian Ocean, which means this air has no access to get into the interior to cause wet conditions. But here, the invasion layer is uplifted and the warm moist air is going to get to the interior and cause rainfall over the interior. So this is a sketch for winter situation. That is why we have dry conditions. The invasion layer blocks the incoming warm and moist air. In summer, there is weaker descendants. The Kalahari is vertically displaced and is not very active over the land surface. So the invasion layer is uplifted and warm and moist air from the Indian Ocean will get access to the interior. Right, number 1.51, definitely that one we have pre-discussed it before when we're looking at the valley climates. So just to repeat it, we can say it's the reversal of the normal temperature gradient. Our normal temperature gradient, we know that temperature should decrease with altitude. But if temperature increases with altitude, that is an inversion. Or we can say it's when a layer of warm air forms over a layer of cool air. Like what you are seeing, there is a layer of warm air which is above. And this warm air here is the inversion layer. Right. We move on to the next question. Which sketch is A or B represents the winter season? Winter season, we've talked about that. This sketch here is winter when the inversion layer is lower and is blocking the incoming air. Right. 153. Provide evidence from the sketch to support your answer. The evidence I've already given. The evidence is that the invasion layer is below the plateau. You can see here the invasion layer is here. This whole layer is touching the plateau, is even below the plateau. And what will happen is blocking the incoming warm and moist air. That is why we have dry conditions over the interior in winter. Warm and moist air cannot reach the interior because it's blocked by the invasion layer here, which happens in winter. Explain the likely stable conditions experienced in the interior of South Africa in sketch A. Stable conditions, we are having anticyclonic conditions. There is no formation of rainfall or precipitation. It's a stable condition. If we have dry interior, the interior is dry, we don't have cloud formation. The absence of clouds over the interior or the clear skies, which is caused by strong descending air. When air is descending, it cannot form clouds. Clouds can only form when there is upliftment of air and condensation takes place. So that descendance of air will lead to clear skies over the interior. It's one typical stable condition. And also we have a dry interior. There won't be precipitation. Why again? Because the warm and moist air which is supposed to feed into the interior to create rainfall is blocked. So those are the typical conditions that we experience. We have cloudless atmosphere over the interior, and also we have the dry conditions over the interior. A farmer in Free State wants to plant crops that require large amounts of water. Explain why the climatological conditions depicted in sketch B would suit this type of farming. Our sketch B here is allowing warm and moist air. Why would this suit the farmer to produce crops that require large amounts of water? Basically, the question is asking about, explain how would we have high rainfall being experienced over the interior because of the situation happening on that sketch. The situation will explain that the invasion layer is above the plateau. You can see that is there. Why is it above the plateau? Because there is weaker descending air. This Kalahari high pressure cell is not active, it's not strong, it's failing to push the invasion layer downward. So what the implication? Warm and moist air from the Indian Ocean is going to access the plateau. It's going to reach the surface. What is it going to do? It is going to cause wet conditions over the interior. Condensation will happen, clouds will form, and we'll experience precipitation over the interior. And what is going to happen? If there's precipitation, it means the farmer is going to produce as much crops as is possible because there's sufficient precipitation or there's sufficient moisture for the type of crop that they want to grow. Or you can relate to the traveling disturbances in summer. We can have line thunderstorms forming, which produce very heavy rainfall over the interior because the invasion layer is uplifted. So basically that is what you relate to and how you relate it to the given question. Right, that was question number 1, which is a climate and weather. We move on to geomorphology, which is question number 2. We are looking at the river's longitudinal profile. Right. Question number 2.11. The longitudinal profile in the diagram represents A or N river profile. If you check here, we have this and we have that. We have this sudden drop in gradient which we are experiencing here. Our river channel seems like it's smoother from there, but here we have a sudden fall in gradient, then it continues like that. What kind of profile is this? If we are to relate to river profiles, right? This qualifies to be an ungraded profile, which is Z. Ungraded, we are saying the river does not have a smooth concave shape from its origin as it goes towards its until it reaches its mouth. So it's ungraded. The river course indicated by X on the longitudinal profile is in which course? By X you can see from this starting point until somewhere there. So predominantly it's in the upper course. In the upper course we know that there is steeper gradient, the river channel is still small, and we have the V-shaped valleys, whatever. These are somehow visible there, like the steepness. You can see the landscape is very steep, and also the channel is still so smaller. Right. Then number 213. Let's check 213. Erosion is the dominant, says dash erosion is the dominant erosion process at X. If you say at X, we are still in the upper course. Remember the 3 types of erosion that happens in the river channel. We have vertical, lateral, and headward. Right? Vertical erosion, we are saying, is the type of erosion that is responsible for deepening the river channel. When the river channel becomes more and more deeper, it's because of vertical erosion like this. The river channel keeps on getting deeper and deeper, that is vertical. Then lateral, we are saying the river channel is like this. It erodes sideways, it becomes wider. Sideways, it becomes wider, that is lateral. Then headward, we are saying the river source is there. There is erosion, the river source migrates, is now there. The source is there, the source moves there. At the end, the river becomes longer. So headward, lengthening, lateral, widening, vertical, deepening the river channel. Those are the three basic types of erosion that we experience in a river channel and through river processes. Right. So the correct response for that one is vertical. In the upper course, that is where we have vertical erosion dominating. We have lateral in the middle course. Then we have vertical and headward happening in the upper course, and then lateral dominating in the middle course. Then the sharp drop in gradient indicated at B at this point here. The gradient is sharply falling. That is a waterfall. Right, we go on to the next question, number 215. Dash erosion may result from the removal of the temporal base level at B. Removal of temporal base level at B. If B is removed, the river now becomes a dash erosion may result in the removal of the temporal base level. The temporal base level, we are saying it's a waterfall. If it's like this, water is flowing from there, is plunging down and continues. How can we remove this? This one here, you can see the water, if you check it, the waterfall, we said it retreats upward. It retreats up the stream. So what kind of erosion which can be responsible for the retreating of the waterfall up until it reaches a grade? That is basically because of the effect of headward erosion. This waterfall will keep on migrating. This part crumbles, this part crumbles, this part crumbles until we have a grade. So this temporal base level is going to be eroded headwardly and until the river attains a smooth concave shape. Then the number 216, after the removal of the temporal base level, when it is removed, it's giving us a nick point here like this. The river is starting from there, it's going down, it's continuing. If it's removed, the river becomes a smooth concave like this. So it's Z for that one. Then the last one, the flow is predominant on the slope of the river profile as indicated at S. And if you check at S here, we are in the lower course of the river. We are feeding into the mouth, which is the sea. So we have two types of flow. This is what we call the laminar flow, and this is what we call the turbulent. Turbulent, we are saying the flow surface is not even. The water is plunging up and down and is having an uneven flow. But if the flow surface is smooth, the water will flow quietly. So what is likely to happen in the lower course? In the lower course, we are likely to have this kind of flow, which is Y, a laminar flow, where the water flows quietly through the channel, because now there is less of erosion happening there, which will make the surface uneven. The surface is more even because there is less erosion taking place in the lower course of the river, and the river flows quietly. The turbulence is mainly realized in the upper course because of the dominance of vertical erosion, which makes the surface uneven, and as a result, the water will be plunging up and down as it flows through the channel because of the incidence of vertical erosion. Right, move on to the next question. A drainage pattern that is formed as a result of melting ice is known as, when ice melts, it creates a drainage pattern which does not have a definite shape. So the correct response is deranged. Then where number 2.22, A or N drainage pattern does not match the geology and topography of the surrounding landscape. Which one doesn't match? Right, the correct response is superimposed. Right, we're going to explain between the superimposition and the antecedents. How do those two differ? Right, when a drainage system is superimposed, It means it's put onto a new landscape. Initially, the river was somewhere on a higher ground, and maybe there was a landscape here. Maybe there is a landscape which is underground. The river's original position is up there, but because of erosion happening, the level of the river is going to get lower and lower until it gets into contact with this landscape, and it's going to effectively erode the landscape. That is superimposition. The river is being brought to a new landscape which was existing, which means the landscape was there before the river. The river is the one that visited the landscape. The landscape was there but was hidden, maybe underground. But because of continued cycles of erosion, the level of the river's flow kept on declining until it got into contact with that particular landscape. And the river is now managing to erode through that landscape. So we are saying it does not match the geology of the topography, because the river was not there before, the river was there after the landscape was existing. Then we have antecedents. This is a system that existed before the current landscape was formed. The river was there, the landscape was not having that shape. Maybe later on there was isostatic uplift, or maybe there was a folding that took place, and that river maintained its course. It means now the river is older compared to the landscape. Superimposition, the landscape is older than the river. The landscape was there, then the river is the one that visited the landscape. The river was somewhere else, while the landscape was there. But because the river was reduced, maybe because of cycles of erosion, the river got into contact with a previously hidden landscape. So it's superimposition. The river was imposed to some landscape which was existing on its own. But antecedents, the river was there and the landscape was not like that. Maybe the landscape was isostatically uplifted, or the landscape was folded and then the river managed to maintain its course through the area which is being folded. That's the difference between the two, antecedents and superimposition. When we get to the question of antecedents, I think you will be understanding what we mean. Right, so we go to number 223. The following characteristics describe the dendritic pattern. Dendritic, let's not waste time. You know how dendritic looks like. Is a tree and its branches. The tributaries, they join the main stream at acute angles like this. This means the stream is going in that direction. The tributaries are joining at acute angles, and they are resembling a tree and its branches. The correct response for that one, for 2.23, is response number D, which has got item 1, join at acute angles, and branches resemble the trees, the branches of a tree. So correct response here is D. Right, move on to the next question. Right, 224, we have explained this. This is antecedents. The pattern occurs where a river maintains its course. The river is managing to maintain its course despite the area changing its form. The area is being uplifted, but the river was there before the upliftment, so it resists and maintains its course. Right, number 225, based on those two, drainage pattern represented by A is the difference between A and B. I think you can see these streams are originating from a focal high-lying point, radiating in different directions, and these ones are starting from the surrounding high-lying area and feeding into the low-lying focal point, which lies between amongst on the center of position of the area. So that's the difference between these two. This is radial, this is central pattern. Right, drainage pattern at A, we've answered that A is radial. Drainage patterns A and B develop respectively. Respectively, we are saying in that order. The first response is answering A, the second response is answering B. So the correct response there is response number 226B, a dome and a central basin. What is a dome? For example, we are talking of a volcanic dome. We are saying it's a high-lying area. For example, a volcanic mountain. Right. If it's a volcanic mountain, maybe with a caldera on top of it, maybe the streams are starting from the caldera focal point. Maybe there's a dam on top of a mountain here, and then streams are starting from that, going into different directions. This is a dome. they are starting from the focal point, which is high line. All streams are starting from here, radiating in different directions. But when we are talking of the central basin, we are saying this is a low-lying area, and the surrounding area is high-lying. Streams will flow and feed into this. So this is the correct response. These ones are radiating from a dome. These ones are feeding into a central basin. So the correct response is B. Move on to the next question. Right, 2.2.7. Based on those three sketches, let us explain them before we answer the question. When we are looking at density, we are looking at the total length of streams in a drainage basin, or we are looking at the total number of streams in the drainage basin. If we are looking at the length, we are saying if we are to accumulate or join those streams, all of them to make them one, how long are they going to be? That is the density. Or if I are to look at the numbers, we are counting 1, 2, 3, 4. How many are there in that drainage basin? So high density, we are saying we have so many streams in terms of number. Or if we can accrue them to one, they can be having the longest length. That is high density. And then we have low density. It means the opposite. The streams are fewer, and if we can accumulate them cumulatively, it will mean that their length will be relatively shorter. So this one is a very high density basin, C, and this one is a very low density, D, and E is a medium density if we are comparing the three. Right, let's go to the questions. Arrange the sketches A, D, and E according to the increase in drainage density. We have explained that. The correct response is the lowest density is D. We move on to E, we go to C. So DEC is the correct response, which is D. The drainage density in sketch C represents a drainage basin in a region with dash gradients and dash permeability of rock structure. If you look at sketch C, that is the highest density. In terms of steepness of the area, for us to have high density, we need a steep sloping landscapes. For streams to form, we need surface runoff and less infiltration. So how do we experience more surface runoff in terms of gradient of the landscape? The area must be steep so that the raindrops cannot have time to filter into the groundwater storage, but rather they flow over the surface and create more streams. That is with the steepness. So it's the opposite. Where there's flat land or where there's land is gentle, we have less or we have low density. Where we have steeper gradients, we have more density. And looking in terms of permeability, we are saying the underlying rocks allow for the moisture to filter or rainwater to filter into groundwater storage. If the rocks are disallowing, it means in that particular area, we tend to have a high drainage density because much of the water cannot get into groundwater storage, but rather it finds its way on the surface, creating more streams. But where they are permeable or where we have porous rocks, those rocks will lead us to having a lesser density because the moisture is going to, the raindrops are going to filter into the earth surface, into the earth groundwater storage and lead to low density. So the correct response is that one of steep and low permeability, which is a combination at A. Then we can move to 2.3. Define the concept of braided river channel. A braid, it's a stream that has got a multiple interconnected channel. So we are saying a braided stream, it has multiple interconnected channels, which also has what we call the temperate islands, or what we call the sediment bars. What are we saying here? We have one stream. This is one river channel, and in this same river channel, we can have an island here, or we can have a sediment bar. These are deposits which are happening, but they are happening inside the channel. At the end, the water is forced to split. Coming from here, it splits in that direction. It becomes a channel on its own. This one becomes a channel. This one becomes a channel. It goes, continues, becomes a channel, continues here. but we are saying they are interconnected, meaning to say they are meeting with each other. This one is splitting here, but they are ending up meeting there again. Splitting there, they will end up meeting, splitting and end up meeting, but they are split by these deposited materials which are constituting to some islands within the river channel. So that's basically the braided channel. It consists of multiple interconnected channels or islands and sandbend bars within the same channel. Right, that is a braid. Right, we move on to 232. Identify fluvial or river features A and C. Right, we'll quickly check on A and C. If you check A, you can see that this is the flat lying area adjacent to the river channel. Definitely A constitutes to be a flat plain. It's a flat land adjacent to the river channel. This area here is flat lying and is adjacent to the river channel. So A constitutes to be a flat plain. And what about C? C, you are seeing where it is there. That one. It's deposited material which is accumulating within the river channel. So that one, you can call it a temporary island. Or we can call it a braid bar. Or a sediment bar. It's sediment, meaning to say it's deposited material which is accumulated within the river channel, creating some form of an island, but it's a temporary island, can be eroded at some other point in time. So it's a temporary island. It's an island which is formed because of deposition, but if the river regains its energy, it can take it away, or it can erode it away. That is why we're saying it's a temporary island, or it's a sediment bar. Right. Then we move on to the next question. The next question is on give 3 pieces. Choose the correct answer from the options within the brackets. The upper, middle, or lower fluvial courses is depicted in the sketch. Right, if you check this course here, the features that we have are the braided channel. We have braids starting from the middle course going towards the lower course. Because we are saying the braids are formed because predominantly there's more deposition than erosion. So starting from the middle course going to the lower course, you tend to find that that is where we have formation of depositional features. But predominantly the braids, we can say they are more of middle course features, because in the lower course we have more pronounced features that form there because of excessive deposition. Like when you talk of the deltas, those are typically depositional features that we tend to experience as the river is in its lowest course feeding into the mouth. So basically this one can qualify to be a middle course. And then we go to the next question. 3 pieces of evidence from the sketch to support your answer. What are we seeing here which make us believe that this is typically a middle course part of the sketch? Right, we can look at over this one here. If you are to look at the width of the flood plain, the flood plain is more pronounced, is wider, meaning to say we have overflowing of the channel and feeding onto the adjacent land. This can happen in the middle course and not in the upper course. We have a wider flood plain, and also if we can check there, we can look at the gradient of the landscape. The gradient is basically general in that area by having a flat, generally flat land where the river is overflowing. It's not steep. There is general gradient there. It can also be a factor. And also if you check the stream channel, we have a wider stream channel, resembling that there is some form of lateral erosion taking place in that area. Right, let's move on to the next question. Draw a freehand labeled cross section along a B to C. Our B is there. You are seeing that B is a higher lying area and there is some form of a terrace here. It's sudden dropping gradient, then we go to a flatland, and again there's some form of a terrace here. for us to get into the channel. And from here, we are having a heap of deposited material, which are also giving us some form of a this sediment bar. And we have another sediment bar here, you can see. So if we are to look at the nature of the gradient, this is a high-lying area which is higher than any other area here, which is potentially higher. Then there's a terrace here, we go down, we go on over a flatland, then we get into the channel, we had this deposited material, and lastly, we had the deposited material at the end on C. So drawing our sketch from C, a simplified sketch, it means if you are coming from B, if we are to put our B here, and it means we are coming from somewhere flat, and we go down. Then we get another flat length, which is the plane, go down, and we now get into the channel. But as we approach C, we first of all reach this deposited material, and we continue, we reach the last one, where we find our C. So basically, if we are to look at this, that is basically how the cross section is going to look like. We have something like a flat length from B, slightly smaller, then there is some form of a terrace here, then we go to the flat plane, then we go to the channel. But within the channel, there is the accumulated deposit here, which is this one. And again, we get back to the channel, which is lower, and again we have another set of accumulated material or deposits here. So basically that will be the shape of our cross section if we are to draw from a river from B to A. And if we are to put labels here, we can now indicate that this is some form of terrace, and this is the flood plain, and this is now the channel. And within the channel, we have this sediment bar here, or the temporary island. And again on C, we have another island. So that is basically how our landscape looks like if you are to draw from B to C. We have those features are being as we are seeing them from here until we get to along the line B to C. That is basically how we can sketch that one. Right. We move on to the next question, which is explain why tourists should not set up a camp at point C. If you are a touring person, you have toured the river, you wanted to explore whatever is happening in the river, you are advised not to camp at C. Right, the first reason, because we have mentioned that this is a temporary island. It's a qualifying factor that you cannot camp on a temporary thing. Temporary thing can disappear at any point in time. It being temporary, it's at great risk, or it's prone to flooding. It's very prone to flooding whenever there is high discharge from up the stream. So it's not advisable. That feature is temporary. It's not permanent. And as you can see, it is within the river channel. So it being not temporary and it being within the river channel, it also means that there is high risk that if there is a flood happening, which might have happened upstream, they are going to be swept away while they are on this temporary feature. Let's go to this one here. It's on stream pirates. Define river capture. I think what is important here is for you to indicate that there are two rivers, and those rivers, what differentiates them is their energy. River capture is when a more energetic river, in this instance we are saying one river has got more energy, a more energetic river intercepts. That is what is important. Talk about the energy. What does the more energetic river do? The more energetic river, it intercepts. Use proper geographical terms. Interception. It intercepts what? The headwaters. Headwaters meaning to say water coming directly from the source. Headwaters of what stream? Of a weaker stream. That's the process of piracy. A more energetic river intercepts headwaters of a weaker stream. That's basically in simple terms. That is how you can define river capture. Or a more energetic river intercepts the headwaters of a less energetic stream. That is stream piracy or river capture in simple understanding. Right, let's move to the next question. Provide a geomorphological term for the features indicated, labeled a highlying area labeled A and a resultant feature of river capture labeled B. Highlying area labeled A is this one here. You can see there is one river here, Mhlapise, and Klitaba is here, and there is a highlying area which is separating those two rivers. A highlying area which separates two distinct river systems or which splits two drainage basins is called a watershed. So that is a watershed. It's separating two distinct basins or two distinct river systems. A resultant feature, and also what you should note here, there is what we call a watershed and what we call an interfluve. Those two are usually confused for each other. An interfluve, we said a watershed separates two distinct rivers, which means those rivers are different and they have got their own tributaries as independent streams. But an interfluve, it's a highlying area which is separating two streams, but those streams are within the same drainage basin, or they are streams of the same river system. If you have a highlying area that separates two streams within the same, for example, like this, we have this stream, it has a tributary here, here's another tributary here, and there's a highlying area here. This is an interflow. Is splitting stream A from stream B, but both streams are within the river system of river Ara. So an interfluve is different from a watershed. A watershed is separating two different rivers, but these ones are streams within the same system or streams within the same basin. Right. So this one is a watershed. Then this one, the resultant feature labeled B. If you check here, this one is a bend. After the piracy has taken place, there is this bend here. This bend is called the elbow of capture. That's the name that we give to that one. It's called the elbow. Elbow, it resembles the shape of an elbow of an arm. So it's an elbow of capture where stream piracy has actually taken place. It has taken place on an elbow, on a bend. So we call it an elbow of capture. I quote evidence from the case study that the misfit stream occurs in area C. Right, area C here, the misfit stream. We are saying this is the stream which sustains or which resumes after stream piracy has taken place. C is continuing, but the headwaters have been intercepted into this stream here. From here, the elbow of capture, the headwaters or from the source is now going to this side, but this one becomes the misfit stream. So we want to quote evidence that the misfit streams occur in area C. Which evidence do we have which talks about the presence of the misfit? Right. It says here, Mhlapise, deprived of its previous strong flow, is now a soggy and confused and uncertain way to gather its strength down the distant elephants. This statement here implies a misfit stream. It has lost its original supply of water. Its headwater supply had been lost. So what is it? It's deprived of the previously strong. It was previously strong when it was having its headwaters, but that's now history. It's no more there. And now it's become a soggy and confused. It has lost its water supply. It's now confused. It's now a wetland which is confused and is uncertain of how it will gather strength. It's now very weak. It's no longer having its strength because its water has been intercepted. So it's now weak. That is basically where we capture the quotation which links us to the response to that question on the misfit, which is talking about the stream which is trying to keeping on existing after the process of piracy has taken place. Right. Then we move on to the next question. The next question is based on what? Describe the impact or discuss how the flow characteristic of Great Letaba River will change after river capture. After the process of capture has happened in the Letaba River here, what is going to happen to the flow characteristics? Right, the question is asking about flow characteristics. What is going to happen to the flow features of the river? How is the flow going to now appear like? You need to relate to the flow of the river. So what you need to note there, this one here is captured water from the weaker stream. It means automatically its flow feature will now be having high discharge. It's now having high discharge. Why does it have high discharge? Because of the headwaters captured. It has managed to capture headwaters of another river, and now it is having high discharge. There's now high discharge in that river because of the captured headwaters. Or it is now having high volume. The volume of the river is now high because it has captured headwaters. It is now additional water from the headwaters of the weaker stream. And you can also talk of its erosive feature in terms its flow feature in terms of its erosive power. What is going to happen to the erosive power of the river? The river is going to have more energy, or is going to rejuvenate. I think you understand the rejuvenation, where the river regains its energy to cause vertical erosion. This river is going to get more erosive power. It's going to cause more erosion on its channel because of increased energy from the headwaters captured. And also deposition is going to happen to the deposition. There's going to be less deposition because of the increased velocity of the river. Deposition will only happen if the river's energy falls below the minimum required to transport a given set of load. And also what is going to happen to the velocity? We talked about volume. Velocity definitely is going to increase. The river will become faster in terms of its flow because of re-energization which comes from the headwaters captured from the other stream. So when you're looking at a flow characteristic, relate to the discharge level or the volume, relate to its capacity to erode, relate to the level of deposition happening, relate to the velocity of the river. Those are the key features that you should address. And when you're talking of flow characteristics as being affected by the process of river capture, and you should be able to relate to describe how they happen to change after the process of capture has taken place. Now to move on to the next question, describe the impact on farming activities along the Mohlapitse River after river capture. What is going to happen to farming activities? We've seen that the flow features of the river are attributed towards the favor in terms of the discharge of the river and the volume. How is that going to impact on farming? Definitely we are going to look at the other side of the river, where the river has lost its discharge, because we are looking at this side here for this question, and we are looking at the flow features is the capture stream. There is more velocity on this side, but we are looking at what is going to happen on this side here, where the waters have been captured. What is going to happen for this poor stream whose water has been captured in terms of farming? Right, we'll look at activities like agriculture are going to be disrupted. There's going to be less water for irrigation, which means it's going to negatively impact on farming activities. The headwaters are captured downstream. There's less water for irrigation purposes, and that is going to contribute towards reduction in the farming capacity in that area. And also you can look at reduced yields. Yields are going to reduce because of limited water downstream. We're going to have poor yields there because the amount of water needed to support the crops might be limited now because of stream piracy. Or we can talk of reduction in the farming profits. Reduction on the profits for farmers downslope because of the capture which has taken place. Or you can look at reduction in the variety of crops grown. the crops grown in the downslope, the variety can be reduced, or you can talk of the general farming activities can be affected negatively. They can be reduced because we cannot keep on producing more given that the quantity of water to support those crops has been impacted by the process of stream piracy. Those are some of the relevant responses. We move on to the last question on geomorphology, which is a question on river management. Right, river management as a concept, before I read that text, it's a text for you to study. Right, we're talking of river management. We are looking at what you should address here. You should just try to touch on some key concept on river management. Right, it's planned and it's coordinated. It's not just something that can be done anyhow without a fixed plan. We need to know what is happening and we need to implement strategies on how to deal with the problems. And it should be coordinated, meaning to say different stakeholders should have a common understanding and they should have the will of working together towards attaining whatever is required on the river. So it's a planned and coordinated action which is taken to manage and regulate the use of rivers or use of river resources and protecting the river ecosystems and the surrounding environment. Our target is we want to protect the river resources. We want to protect the river ecosystem and we want to protect the surrounding environment on the river. But how? We have to plan for it and coordinate it, work together. That is river management. So it's planned and coordinated action which is taken to manage and regulate the use of river resources and protect the river ecosystems and surrounding environment. That's the geographical concept. You can define it in your own understanding, but it should address the basics of managing a river. It should address of taking care of the rivers. It should address the basic concept of conserving our river resources for the benefit or sustainable use of our river resources. That is basically what you should address. Right? What is the main source of pollution which resulted in the closure of beaches? We are told that the beaches were closed here, and we are looking at sewage leaks which are being talked about there. That is the major cause of the closure of those ones is because of raw sewage which was leaking. Then court evidence from the article that suggests that the lack of infrastructure maintenance resulted in the pollution of the rivers. Right? If we come to our text here, we find there's a section which talks about critical infrastructure. We'll check here. Right, it says the roads and critical infrastructure, including a number of water treatment plants and pipes, were damaged in the last season of flooding and have not yet been repaired. That is where we get our response. The response is relating to a lack of maintenance of infrastructure and is contributing towards pollution of the water bodies. So mainly the pipes which were damaged and were not replaced. It means those water treatment plants and their pipes, they are leaking sewage into the rivers and they are causing pollution. Right, quote evidence from the article, we talked about that, number 254. What impact might the pollution mentioned in the article have on the natural environment? The pollution mentioned here, we have the impact which is indicated here. It says it's exposing pathogens in wetlands and aquatic ecosystems. That is the natural environment. Now, looking at the natural environment, we are looking at the environment which is not man-made. If you are looking at the wetlands, they are natural, and the aquatic ecosystem, they are negatively impacted by the exposure of pathogens from the raw sewage as it gets into contact with the wetlands and the ecosystem of the surrounding river systems. Right. Then we go to the last question. The last question is basically based on strategies that can be implemented by the Gauteng municipality to reduce pollution. Right. I'm going just to highlight on the strategies. You know the strategies, they are general strategies that anyone can come out with, but you need to validate those strategies. Come with a fixed geographical point, a meaningful geographical point, and try to explain on that particular point, try to elaborate and make sure that the point is well understandable and makes much geographical sense. right? We can talk of repairing of infrastructure. For example, we have seen that the problem that we are experiencing here is caused by the leaks on infrastructure which is not maintained or which has been damaged previously during flooding and has never been maintained until now. So we should repair infrastructure to avoid sewage leaks. And then we can also educate people. Education is a very crucial tool which can be used. Sometimes the people, they damage the environment out of lack of knowledge. They do cause pollution into water bodies out of lack of knowledge. So if we do awareness campaigns and we do educational programs to educate the citizens on the dangers of harming the environment or on the dangers of harming the water resources, then they can take preventive measures and precautionary measures against such activities. Then we can also talk of collaborative governance. Collaborative governance, we are saying, when we are doing collaborative governance, remember we said when we are defining, we said it needs to be done in a coordinated effort. So here we are looking at collaborated effort. It's not only the municipality which should take initiative, it should collaborate with other stakeholders. For example, businesses. Businesses can also be encompassed in the process of conserving the resources, the rivers, and they can contribute resources. Or engaging the church community, engaging whatever community, engaging the local community, engaging whoever is there, so that we work together and attain the desired goal. So we need collaborative effort. The municipality should try to work with other stakeholders responsible or other stakeholders concerned, so that there is one voice towards restoring the water resources which are damaged. Then we can also talk of restoring natural habitats. And also we can look at habitats like the wetlands. Though they are damaged now because they are pathogens exposed, but we can take a corrective measure. We can restore them, try to bring them back to use, try to bring them back to good environmental use. We can reclaim and restore their quality. And also we can talk of legislation. We can use the law. Implementing legislation against environmental damage or against pollution of rivers. We institute laws. The municipality implements or puts in place some regulations to ensure that there are laws against damage on the environment. And also, besides implementing such laws, they need to be enforced. It's also another strategy. Enforcing them. Instituting a legislation is different from enforcing it. There are so many laws which are in place which are not being obeyed fully because they're not being enforced. So if there is a legislation, then there's a follow-up on enforcing it. Then that can work and solve typical problems associated with those challenges of river pollution, which come from the problem of poor river management. Right. So basically that's the picture of the section of geomorphology. If I'm to comment on the content that was required in the paper, or to comment on the level of difficulty of the paper, I would comment it as a fair paper. For an average learner who has studied, or for an average learner who is always studying, this paper, I see it as an average paper. You cannot say it's a difficult paper, though we cannot say also it's a very easy paper. It's not very easy, but it's not a difficult paper. It's basically a fair paper if I'm to take it from the perspective of an average performer, which will imply that I expect maybe learners attaining grades which are maybe ranging from level 5s and level 6s, and the distinctive one always getting their level 7s. But basically the nature of the questions, they are clear and they are straight to the point, and also the content covered is relevant and very straightforward, and also the wording which was used, the words which were used in designing the questions, they are also not disadvantaging the learners in any way from the way I assessed the questions. Right, then we move on to our last section, which is the map skills and calculations. Right, the map that we are using for this discussion is a map based on the topographic map. First, as usual, it's an extract 3026 DA Aliwal North, and the orthophoto map is an extract from the topographic map, which is extract 3026 DA 19 Ducatole. Right, and as usual, you should remember that our maps, they are drawn into according to the two different scales. We have the scale for the topographic map, which is 1:50,000, and the scale for the orthophoto, which is 1:10,000. Right, we go to the first question on map skills. Remember, map information, we should read the map information provided on your question paper. There is map information which is very relevant, which will help you answer some of the questions. That information is not provided for you just to see and ignore. You have to read the map information. It gives you the details about the place. So you can use that information to answer some of the questions in the question section. Right, the first question is saying, in which province is Aliwal North located? The response is in map information. It says here, Aliwal North is a town in central South Africa on the banks of Orange River in the Eastern Cape province. So the response is there in the map information. So our correct response is the Eastern Cape according to the map information. You might not get to know all places such that you can ignore the map information. It's not everywhere that you know in South Africa that you can say you can afford to ignore a map information. Right. Then number 312, coordinates for Aliwal are 30 degrees and 42 degrees south. Then 26 degrees and 42 degrees east, that is longitude. The 30 degrees south referred to, automatically I have given the answer. When you are giving our coordinates, is latitude to longitude. So it's degrees in latitude and minutes in latitude. If you are to give exact location, we add the second value to the south. South African places are to the southern hemisphere, south of the equator. So we name our latitude and our location as south. Then in terms of longitude, it's 26 degrees, 42 minutes. If you are to be precise on a particular feature, we add the second value and we name it E, which is east, which means South Africa again is on the east of the prime meridian. Places in South Africa are named south in terms of latitude and are named east in terms of longitude because we are in the eastern part of the hemisphere divided by the prime meridian. Right, we move on to the next question. So this one, the correct response is latitude. Calculate the area in square meters of the graveyard in block D1. The length is 1.1 centimeters and the breadth is 0.7 centimeters. So if you check here, the graveyard is given, it's in block D1 on the topographic map. Maybe just seeing it, but it doesn't matter much seeing the graveyard. The graveyard, I think you can see it's here. This is where our graveyard is, according to the reference given there. I think we can figure out the symbols that we have here. The symbol for a graveyard, you can see, is this one here. A polygon feature with some crosses on it, which imply that maybe those are the graves inside that graveyard. So you are not supposed to do anything with this graveyard. It's already there and the measurements are already indicated. There was no need for you to measure anything on that graveyard. You were just supposed to do the calculations. Right. You have to do direct calculations for you not to confuse with the conversions. If you have your conversions written aside, that is going to help you and won't confuse you if you are not very mathematically talented. Right. What you should note is, if you are someone who is not very good with mathematics, what you should do before you attempt any questions, play around with your scale so that you know your conversions. Right, for a topographic map, if anything is coming from a topographic map, the scale is 1:50,000. And you know that whatever measurement you get from the map, you have to multiply it by 50,000 to get the actual ground distance. So if there's need for conversion, what are you going to do? You know that you're going to use your ruler and you're going to measure your distance in centimeters. But how are you going to play around with the measurement so that you don't confuse yourself to convert them to other units of measurement? Right, if you are using your measurement and you want to convert it to centimeter, multiply it directly by 50,000. You get your actual distance in centimeters. If you want to convert it to meters, you multiply directly by 500. Your answer will be in meters. Whatever measurement you get from the map, multiply by 500, your answer is already in meters. If the question is asking about conversion to kilometers, what you should know is you should multiply directly by 0.5. Your answer will be in kilometers. That is when you are dealing with a topographic map. If the question is coming from a topographic map. If it is coming from an orthophoto map, again, you should know your scale and you should play around with your scale so that you don't waste much time doing calculations of conversion from centimeters to meters, meters to kilometers. That is going to consume more time and will end up confusing you if you are not that kind of person who is good in maths. So what you can do also here, if you get any measurement from the topographic from the orthophoto map and the question requires you to present the answer in centimeters, you multiply directly by 10,000. Then if there's need for conversion to meters, you know that you have to multiply by 100. And if you need to convert to kilometers, you multiply by 0.1 kilometers. Your answer, if you multiply by this, maybe you measured, you get your answer as 3 centimeters. The question says the distance must be in kilometers. Multiply it by 0.1. Directly, you have converted that distance to kilometers. If the question is saying into meters, it's from the orthophoto map, it's 3 centimeters. The question wants you to convert that into meters. Multiply by 100. You get your 300 meters directly. Right. So these are the conversions, the common conversions that you should just have, or you should just write them aside so that when you are doing your calculations, you know directly which one to pick from and which one to use in any given scenario. So if you go to our question here, we just come here. Our breadth we are given, length is 1.1 centimeters. We multiply by the meter distance. This is from a topographic map. We multiply this by 500 to get our breadth in meters. 1.1 times 500 gives us 550 meters. This is our breadth. Our length, we go to our breadth is 0.7. We are given already centimeters. We multiply this by 500. And this is going to give us 0.7 times 500, going to give us 350 meters. And please don't leave units of measurements like what we have discussed before we did the paper. Then you simply multiply these two for you to get the area. If you multiply 550 by 350, you will get 192,500 meters, square meters. Your answer is supposed to be square meters. You are multiplying a meter value by a meter value. That is going to give you square meter value. So 192,500 square meters becomes your response to the area of the graveyard as shown in the topographic map. I'll move on to the next question. Calculate the true bearing from trigonometrical station 56 in block C2 to spot height 1398 in block E2. Right, you're also supposed to be very articulate when it comes to the measurement of that bearing. Right, I have done the drawing for you on the map. Remember, when you're drawing your true north direction, we said our true north direction is any point which you can draw on the map which coincides with the direction of the North Pole. So how do you determine it on the map? You just draw a straight line which runs parallel to your lines of longitude on the map. And once you have done that, you have drawn your true map, your true north. So our true north is there. Our feature is here. You have to draw the straight line connecting the feature directly. Our trig station is here. The question is saying from the trig station, our trig station is there. Your line should be parallel to this, meaning to say the distance from here to there should be the same distance from this longitudinal line to there. Or if you are to use this one, distance from here to here should be the same as the distance from here to here. Then you identify the other feature that you want to calculate, you determine the bearing. It's a spot height 1398. Our spot height, if you check clearly, our spot height is here. Spot height 1398 is here. So what it means is, after identifying the spot height, you have to connect by drawing a straight line which links your feature from where you are starting and link it to the feature where you are supposed to end. And you connect the two. with a straight line, and ensure that you are using a sharp ruler, a well-sharpened pencil, and a straight-edged ruler, not the one that will give you bended lines. Then, what is true bearing? True bearing is an angle which is measured from true north in a clockwise direction between the true north direction and a line connecting the two given features. Our true north, we have seen that is there because we've drawn our true north south line, and it means we now want an angle in a clockwise direction until we connect to a line. Our line is slightly just next to our south line of the north-south line, which required you to be very accurate, because if you would estimate, you would assume that it's 180, but it's not exactly 180. That place, that spot height is not at 180 degrees from the spot height, from the streak station, if you are to draw your north-south line correctly, which means you're supposed to draw your accurate north-south line so that you get the actual size of the angle. And then you place your protractor with your 0 on this side and your 180 coming on the southern direction here. Then you determine where this line crosses the edge of your protractor. You take your reading from there. So it means your 0 on the protractor will be there like this. The protractor ends here. And when it ends here, check the margin of your protractor here and see where that line crosses. Check the value of where that line crosses. According to my calculation here, I got an angle which is slightly plus or minus 177 degrees. So it will depend with your preciseness when measuring. Maybe some might get 178 or might get 176, but it should not vary by plus or minus, but by more than 3 degrees. It should be slightly somewhere around 177 if you are to be accurate with your measurements. So basically that is how you measure your true bearing for those two given points. Right, let's go back to our question paper. Right, calculate the magnetic bearing from trig station 56 is the same reference. We just want to apply the formula of magnetic bearing. As given here, magnetic bearing is true bearing plus magnetic declination. Our current declination, we don't need to calculate it because it's given for us. They have done for us the calculation for magnetic declination and they've provided with it. So we only need to provide our true bearing. We said from our measurements we got 177, which is slightly less than 180 if you are accurate degrees, and we don't have any minute value. Then we are adding 24 degrees and 43 minutes. Ensure we don't interchange the degrees and the minutes. Degrees, they should be added on their own. We add the minutes on their own. So we are adding 00 plus 43. It maintains as 43 minutes here. And what is going to happen to our degree side? We are now adding 177 plus 24. It gives us 201 degrees. So the final response becomes 201 degrees 43 minutes for that bearing, magnetic bearing calculation for that question. Right, proceed to the next question. On the next question, it's talking about why is it important to calculate present magnetic declination. That declination that we are provided, we have to calculate it for the current year. If you want to get magnetic bearing for the year, why is it important? Why can't we just pick any figure and use it? We have to find the precise, and I think you remember you use the map information provided at the bottom of your topographic map to come out with the current magnetic declination from the angle given on the map. So why is it important that we do that? Right, is the main reason there is help us determine the correct direction. When we are doing navigation, we need to, it will help determine the correct direction, because without that we cannot be able to figure out where the correct direction is in the current year. So when we are navigating, it will help us locate the correct direction or the correct location. If, for example, the magnetic bearing is saying the angle is 201 degrees 43 minutes, according to the correct magnetic declination. It means if you are navigating using a compass for compass directions, if you follow that angle, you are not going to get lost. You are going to find the exact or the correct location of where you want to navigate to. But if you use a wrong magnetic declination, for example, you just pick an angle, then it gives you maybe an answer which is 182 minutes. You are not going to get to the same direction because you have used the wrong magnetic declination. Even though your true bearing is correct, but if you use the wrong magnetic declination, your magnetic bearing is going to be wrong. And if you are navigating using a magnetic compass, you are going to get lost because you have used a wrong angle of declination. Because remember, the declination angle always changes. So we have to use the correct angle, and we calculate the present magnetic bearing so that we go to the correct direction, given that we are now following the present magnetic bearing. We cannot follow the same bearing as last year because remember, the declination always changes. So we need to use the present magnetic bearing. If you are to navigate today, you cannot use statistics for 2022. That is going to be inapplicable and wrong, and is going to guide you to wrong places. So basically, that is why it is important for us to follow the present magnetic declination when we are navigating. Right. Then we move on to refer to R in block A3. The dominant drainage pattern in this block is, if you go to R here, R is here in block A3. What is the dominant drainage pattern here? You can see that this stream is flowing here. This one is going there. This one is going there. And this one is also going there through the dam. What kind of pattern is this? The correct answer here must be parallel. Those streams are running parallel to each other. It's parallel drainage system which is being experienced on that particular. So we can say that the correct response here is C for parallel. Compare the drainage density in area R in A3 and S in block B3. We go to our map. R in A3 and S in B3. R is here, we've talked about that, and S is here. Drainage density, we've talked about it. We are looking at the total number of streams or the length of the streams in a given area. This is R, there is less density. There are few streams, we only have a few number of streams, but here there are so many. So S has got higher density and R has got less density. S is a higher dense drained area, and R is a less dense drained area, according to what we are seeing from the map here. Right, we go on to the question again. Provide evidence from the topographical map to justify your answer. Right, we want to justify why we are saying this one is a high drainage area and this one is a low drainage area. Automatically, by looking at the number of streams, we can justify that this one has got fewer streams. There are fewer streams at R here, and there are so many streams at S here. And if you are to accumulate the length, the total length of streams here is shorter when compared to S. The total length of streams here, if we were to add up the streams, they are going to give us longer length. Or if you are to use a geomorphological argument, this is a flatland. Remember, on a flatland, we tend to have more infiltration and less streams developing. So we end up having fewer streams on this area because the area is generally flat. There's only one contour line here, and the next contour lines there are somewhere there where there is this mountain range. But here, this is an eroded area. If you check, or this red indication here, it indicates an eroded area, which means this area most probably is a steep sloping area and is going to have high rates of runoff, and that is going to contribute towards the development of so many streams in that particular area. That is if you are to argue using geomorphological arguments. Right. Then we go to the next question. Refer to tributary T in block B4 and B5 on the topographic map. In which direction is the tributary flowing? Refer to tributary T in block B4 and B5. Let's go to the map. T in block B4 and B5. Our T is here. It's a tributary which is flowing in that direction. This one here, as you can see. Which direction is it flowing? This one is flowing towards the southeastern direction. If you can check there, it's going towards the southeastern direction. Why are we saying so? For us to determine flow direction, we check the tributaries joining that stream. If you check the tributaries here, these tributaries are joining at acute angle facing this direction, which means this stream is most likely flowing in the southeastern direction. And also, if we check, there's a dam here. Where is the wall? The wall of this dam is also going to give us a clue on how the flow direction is inclined towards. The dam wall is on this side, meaning to say water accumulates before the dam wall. So it means this stream is coming from there, such that water accumulates and is dammed by this wall that you are seeing in black color on this part. This water is accumulated, or even if you are using the bigger dam, the wall is on this side, on the southeastern side, which means this stream is coming from the northwestern side, flowing towards the southeastern direction. That is the other argument of these dams. So tributaries, this dam, you can also argue using the altitude. If you check the contour lines or the height around this dam and the height around this area here, this is 1413 meters above sea level, where this stream is most likely to be starting. But if you check around here, this is 1405, and if you check around here, it's 1316. So you are seeing that most probably this is a high-lying area, and as we go down here, the area is gently sloping, going towards a low-lying area. This gives us justification that the river is flowing in a southeastern direction. Then we move on to the next one. We've given the evidence and we've given the justification. Number 323. 323 is saying refer to lines 6 and 7 on block A3 and B3 on the orthophoto map. Draw a labeled freehand cross section from 6 to 7. Refer to point 7. Why deposition is main process taking place. Right, this is interpretation of geomorphology. If you have to look at here, I will draw the cross section there. Right, quickly, when we are doing drawing of cross sections, we are doing a simplified cross section, not a detailed one. We don't need to trace any measure, any heights from the cross section. If we are to put our 6 here and we are to put our 7 here, this is a meander. If you can check, this is a bend along a river channel. The stream is bending at this point. So it means as you're coming from 6, you see the contour lines here. This means it's a steep sloping landscape. What is going to happen as we get into the stream channel here? You need to apply the concept of geomorphology of erosion and processes on the outer bend and on the inner bend of a meander. Then as we go to 7, apply also the concept of deposition that happens on the inward bend of a meander. So from 6, it's steep sloping. It goes down into the valley. In the valley, it curves inside. This is an undercut slope. And then it becomes gentle, going towards 7 like that. This is the nature of the cross section that you are going to draw from 6 to 7. Our 6 being here. And this becomes an undercut slope where there's erosion. This becomes the slip of slope of that meander. Then the next question is saying, we have discussed about the reason for the shape. Yes, that is why they are appearing like that. 7 is the slip of or the inner bend. There is deposition taking place and there's less velocity, meaning to say material is rotated from 6 and it is deposited around 7 and it gives a gently sloping landscape. Let's go to the last part, which is our part on GIS. Basically, what you should note with GIS is basically knowing the concept of GIS. There is nothing much that you need to note under GIS. Application of the basic concept of GIS, that is the main thing that you examined for under the section of GIS. So those concepts, they should be at your disposal of the fingertips, or the GIS concepts, because they are equally important in answering this last section of GIS. Right, let's go to our question paper. Right, identify one GIS process that the farmer could use to identify the best place to graze his cattle. We are told of that farmer on the topographic map who wants to identify the best place to graze his cattle. GIS processes, there are many of them. It now depends with which one he wants to use according to the information that he is interested in. So if you are to look at here, that farmer can use GIS processes like data integration. Integration, we are saying, can bring together different sets of data for him to be able to make a conclusion. For example, he wants to graze his cattle, but the area is steep sloping. He cannot effectively graze the cattle there. It means you need to integrate some data on topography and maybe some data on some other aspect like rainfall. So he needs to incorporate those two data sets for him to be able to come out with a valid decision. Or we can talk of spatial analysis, analyze different spatial areas. Or we can talk of data layering. Can do data layering, compare different data sets and show how they relate to each other and see how he can find a effective grazing area for the cattle. So there are many processes that can be used there, but it will depend with what the farmer exactly wants to do. Right, then name one human-made feature in block A3, in A5, used to extract groundwater. The moment you hear of extraction of groundwater, be mindful, definitely that is going to be a wind pump. That is the main thing that we use for extraction of groundwater. So before you check there, it's saying in block A5, you go to your map, check block A5. Block A5, you can see that it's here, or block A5, in block A5 is here. We have this wind pump here. This is the feature which is used to extract water, so it's a wind pump for that one. Then you check again the other question. Name one human-made feature used to control the flow of water. Again, in the same block, now we want a feature to control the flow of water. If you try to check around here, the only feature that you can rely on, which is a line feature, is this dam wall here. The dam wall is the one which is used to control the flow of water. So this is a line feature, and the dam is, remember the difference there, a dam is a polygon feature, it's an area feature, but the dam wall is a line feature. Then the wind pump is a point feature, is not big enough to be a line feature, it's a point feature. So this question is asking about a line feature, and then automatically that dam wall qualifies to be that feature which controls the flow of water. And then we move on to other questions. This is a question on resolution. Which image A or B illustrates high resolution? If you check here, this image is poorly visible. You cannot see this, and this one is clearer. So the one which is clearer is the one which has got high resolution, and this one is a low resolution. Motivate your answer. Why are you saying this one is high resolution? Why you are saying B is high resolution is because of the amount of detail shown. There is more detail visible in picture B than in picture A. And also you can argue using the pixels. There are more pixels in the image in B compared to the pixels in A. Or if you want to argue using the size of the pixel, B is made up of smaller pixels, A is made up of bigger pixels. That is why it is not very clear, and this one is distinctively clear. That is with resolution, and that is spatial resolution and not spectral resolution. Right, then the last question, explain why images A and B are examples of raster data. The difference between raster data and vector data is raster data is in pixels and grids, while its vector data is in lines, polygons, and point features. So these ones are images. These are real-time images. If you see A and B, these are images which have been taken using a camera technology, and they are in pixels. That is why we are saying it's raster data. If it was vector data, they would come in the form of lines, polygons, and point features as shown on the topographic map. And also be mindful that the topographic map shows details in vector data. In the orthophoto, it shows features in or objects in raster data. The topographic shows the real-time image to which contour lines are added, but that is an area of photograph where we add the other details on height, like we add the other features like spot height, we add trig stations, we add contour lines to those images. So they are real-time images taken using the modern technology of remote sensing, while the topographic maps, they are drawn using the point, line, and polygon features. So that brings us to the end of our discussion. I hope the discussion is helpful enough